and I call it W, I call its value W, so that then I can substitute t instead of x, y, z. So W is, well, let's think of W as a function of three variables, okay? And then when I plug in the dependence of these three variables on t, then it becomes just a function of t. I mean, really my W here is pretty much what I called f before. There's no, there's no major difference between the two. Okay, any other questions? No? Okay. So let's see, here's an application of what we've seen. So let's say that you want to understand actually all these rules about taking derivatives in single variable calculus. So what I showed you at the beginning and then erased basically justifies how to take the derivative of a reciprocal function. And for that you didn't need multivariable calculus. But let's try to justify the product rule, for example, for the derivative. So an application of this actually is to justify the product and quotient rules. So let's think, for example, of a function of two variables u and v that's just the product uv. Okay? And let's say that u and v are actually functions of one variable t. Then, well, d by dt, df dt, so let's say d of uv over dt, is given by the chain rule applied to f. Right? This is df dt. So df dt should be f sub u du dt plus f sub v times dv dt. Right? But now, what is the partial of f with respect to u? It's v. So that's v du dt. And partial of f with respect to v is going to be just u. So you get back the usual product rule. Okay? That's a slightly complicated way of deriving it, but that's a valid way of understanding how to take the derivative of a product by thinking of the product first as a function of two variables, which are u and v, and then saying, oh, but u and v were actually functions of a variable t. And then you do the differentiation in two stages using the chain rule. Okay, similarly, you can do the quotient rule. Actually, let's do it just for practice. So if I give you the function g equals u over v, so right now I'm thinking of it as a function of two variables, u and v, but u and v themselves are actually going to be functions of t, then, well, dg dt is going to be partial g partial u. How much is that? How much is partial g partial u? 1 over v times du dt plus, well, next we need to have partial g over partial v. Well, what's the derivative of this with respect to v? Well, here we need to know how to differentiate the inverse. It's minus u over v squared times dv dt. Okay? And that's actually the usual quotient rule, just written in a slightly different way. I mean, just in case you really want to see it, if you clear denominators to put the v squared, then you will see basically v, well, u prime times v minus v prime times u. Okay. Okay. Now, let's go to something even more crazy. I claim we can do chain rules with more variables. So let's say that I have a quantity, let's call it W today for now. So let's say I have quantity W as a function of, say, two variables, x and y. And so in the previous setup, x and y depended on some parameter t. But actually, let's now look at the case where x and y themselves are functions of several variables. Let's say of two more variables. Let's call them u and v. Okay, so I'm going to stay with these abstract letters, but if it bothers you, if it sounds completely unmotivated, think about it maybe in terms of something you might know, say polar coordinates. Let's say that I have a function that's defined in terms of the polar coordinate variables r and theta, and then I know actually I want to switch to usual coordinates x and y. Or the other way around, I have a function of x and y, and I want to express it in terms of the polar coordinates r and theta. Then I would like to know maybe how the derivatives with respect to the various sets of variables are related to each other. Okay, so one way I could do it is, of course, to say, well, now if I plug the formula for x and the formula for y into the formula for f, then W becomes a function of u and v, and I can try to take its partial derivatives. If I have explicit formulas, well, that could work, but maybe the formulas are complicated. Typically, if I switch between rectangular and polar coordinates, there might be inverse trig. There might be maybe arctangent to express the polar angle in terms of x and y. And then I don't really want to actually substitute arctangents everywhere. Maybe I'd rather deal with the derivatives.